Viewers to the fourth and the last segment of the sixth lecture for the online series of lectures for the course of differential geometry. In the previous segment, we discussed this very useful example of left multiplication on the matrix Lie group GL and R. We'll begin this segment with the concept of immersions and submersions. Let me go straight to the definition. A C infinity map F from the manifold M to the manifold M is said to be an immersion at a given point P in the manifold N. N is the domain manifold of this smooth map F. If its differential at P, which we denote by F star comma P, which is a linear map from the tangent space TPN to the tangent space TFP to the manifold M. If its differential is injective, we want this linear map to be injective, and then we say that F is an immersion at the point P, and it's called a submersion. This smooth map is called a submersion at a given point P if this linear map, its differential at P, which is a map between these two tangent spaces TPN and TFPM, is surjective. Okay, good. We call F simply an immersion if it is an immersion at every point P in N. If it is an immersion at every point P in N, and the submersion if it is a submersion at every point P in N. Okay. So now a remark about this definition. So let me write it here. Remark to the definition of immersions and submersions. Suppose N and M are manifolds of dimension N and M respectively. Then we know that dimension of this tangent space TPN is equal to N, and dimension of this tangent space T sub FPM is equal to M. Right? Now that injectivity of the differential F star comma P which is a map from TPN to TFPM. Okay, and we know that this, if this guy is injective, then F is an immersion at the point P in N, right? So the injectivity of the differential implies immediately that that um, M is greater than or equal to N. Similarly, surjectivity of this linear map F star comma P as a map from TPN to TFPM will imply that N is greater than or equal to M. Okay, good. Thus, if F from N to M is an immersion at a point of the domain manifold N, then M is greater than or equal to N, as we have seen earlier. And if F is a submersion at a point of N, then N is greater than or equal to M, as we have seen here. Okay, so example of immersion and submersion. Example 3. The prototype of an immersion is the inclusion of R to the N into a higher dimensional Euclidean space. R to the M. Okay, so here M is greater than or equal to N. So the inclusion of an n-tuple x1, x2 all the way up to xn is equal to x1, x2 all the way up to xn then all the m minus n entries here are going to be 0. So how many zeros are here? M minus n many zeros. So that the whole thing here is an m tuple. Okay. The prototype of a submersion is the projection of r to the n onto a lower dimensional Euclidean space r to the n. Okay, so that in this case m is less than or equal to n. Okay, so pi is a projection, pi acting on an n tuple, right? So x1, x2, all the way up to xn, and after which comes x m plus 1 all the way up to xn. Okay, this is possible since m is less than or equal to n. So this is an n tuple, and the result is just the first m coordinates, x1, x2, all the way up to xn. Okay, this is a prototype of, this projection is a prototype of submersion. Okay, now another example. Let me erase everything. Example 4. Let U be an open subset of a manifold M, and hence is a manifold of the same dimension, is a manifold. The inclusion map I which is the inclusion of U into M is injective, right? And in general not surjective, right? So there may be points in M um, which don't have any pre-image in the open set U under the inclusion map I. The differential of this inclusion I at P in the open set U, denoted by I star comma P, which is a linear map from TPU to T, and so I of P is just P, right? So this is TPU. This is a linear map from TPU to TPM. Okay. So TPU and TPM are vector spaces of the same dimension, and I star comma P is a linear map between um, uh, these two vector spaces of the same dimension and is bijective, right? Indeed, dimension of T sub P U is equal to dimension of T sub P M, as these two vector spaces are isomorphic. So since this linear map is bijective, uh, the inclusion map I from U into M is both an immersion and submersion. Okay. Okay. So this inclusion map is both an immersion and submersion, which may fail to be a surjective map, right? Because this inclusion map is in general not surjective. So this is an example exhibiting the fact that exhibiting the fact that a submersion need not be surjective at all, need not be onto. Okay, good. Now the notions of rank, critical points, and regular points. Let me erase everything. I'll give the definition of rank and critical and regular points with examples. Consider a smooth map. The story begins with a smooth map between two manifolds. Smooth map F from N to M of manifolds. Its rank at a point P in the manifold N, denoted by Rk F of P, is defined as the rank of the differential, the rank of the linear map, the rank of the differential f star comma p, which is a map from the tangent space TPN to the tangent space TFPM. Okay. Now, relative to the coordinate neighborhoods, coordinate neighborhoods u comma x1 x2 all the way up to xn at p, and coordinate neighborhood v comma y1 y2 all the way up to ym at f of p, the differential f star comma p is represented by its Jacobian matrix, which we have seen in proposition 4. Del fi del xj of p. Okay, this is given by proposition 4. So the definition of the rank of this smooth map F at the point P is just the rank of the Jacobian matrix relative to these two charts, u and u comma x1 comma x2 comma all the way up to x to the n, xn, and v comma y1 y2 all the way up to ym. Okay. So this is the definition of rank. Since the differential of a map is independent, this rank is independent of coordinate charts, so is the rank of a Jacobian matrix. Okay, good. Now the definition of critical points and regular points. Definition: a point P in the domain manifold N is a critical point of the map F from N to N if the differential F star comma P from TPN to TFPM fails to be surjective. Okay. It is, on the other hand, a regular point if the differential F star comma P is surjective. Okay. In other words, P is a regular point of F. P is a regular point of this smooth map F if and only if F is a submersion at the point P. Okay. Now we need the notion of a critical value. A point in M is a critical value. Okay, so a critical value is in the target manifold M. A point in M is a critical value if it is the image of a critical point. Of a critical point. Otherwise, it is a regular value. Okay. So if a point P in M is not a critical value, then it's a regular value. So this is the definition. These are the definitions of critical value and irregular value. Okay. So two important aspects of this definition. Definition. First one, we do not define a regular value to be the image of a regular point, unlike critical values. Critical values in the target manifold are those points which are images of critical points in the domain manifold. Okay, but we don't define regular values this way. So regular values are the points in the target manifold which are not critical values. Okay. Therefore, any point in the target manifold M here in the manifold M that is not in the image of F. Okay, so if I pick up a point from here, from the target manifold M, which does not have a pre-image in N under this smooth map F, is automatically a regular value. Okay, So therefore any point in the manifold M that is not in the image of F or which does not have a pre-image in N under F is automatically a regular value. Okay, good. That was the first point that I wanted to touch upon. Now the second point regarding this definition is as follows. Let me erase everything. A point C in M. So what is the map? F is the map from N to M. A point C in M is a critical value. Okay. So a point C in the target manifold is a critical value if and only if some point in the pre-image under F is a critical point, meaning that there can be points here which are not critical points at all, but we don't care. We want at least one point in this set to be a critical point. A point C in the image of F. Okay, so we rule out the possibility of a point not being in the image of F. You see, so a point C in the image of F is a regular value so we exhaust that options. We cannot have that situation anymore where there is no pre-image um, of this point because this is already in the image of F. Okay, so this is a regular value if and only if every point in the pre-image in this set, every point in this set is a regular point. Okay, good. Now a very useful proposition that we'll use in the next lecture very frequently, I'll state it and prove. For a real valued function, f from the manifold M to the set of real numbers, a point P in the domain manifold M is a critical point if and only if relative to some chart u comma x1 x2 all the way up to xn containing P all the partial derivatives satisfy del f by del x j at P is equal to 0. J runs from 1 to all the way up to n. Okay. So all the partial derivatives of f must vanish identically at the point P. Okay. Proof. By proposition 4, the differential, which is a linear map, f star comma p from Tpn to T f of Pr. So this guy is isomorphic to R itself. This is represented by the matrix del f by del x1 at P, del f by del x2 at P, all the way up to del f by del xn at P. This is a 1 times n matrix. Okay, it is just a row vector containing n entries. So this is the Jacobian matrix with respect to the basis del by del x1 at P all the way up to del by del xn at P. Okay, this is the basis of Tpn. Sorry, Tpm, since F is the map. Where is the map? Yeah, no, F, the differential is this map, right? No, I think I made a mistake here. So this is supposed to be Tpm. Sorry, because F is the map from M to R. So F star comma P is this map Tpm to Tfpr, which is isomorphic to R. So we take the, so with respect to this basis of Tpm, and there is one element in the basis here, which is del y at f of p. This basis of Tfpr. Okay, so this differential is represented with this matrix relative to these two bases. This is the basis of Tp of M, and this is the basis of Tfp R. Okay, now since the image of this differential f star comma p is a vector space, the vector subspace of R. is a vector subspace of R. From this elementary linear algebra knowledge, we know that the image of this the linear map is a vector subspace of R. It is either zero-dimensional or one-dimensional. There are two possibilities only. It is either zero-dimensional or one-dimensional. Okay. In other words, f star comma p, which is a map from TPM to TFPR, is either the zero map, in which case the subspace is zero-dimensional, just the zero vector in R. Okay, so everything is mapped to the zero vector. Is either the zero map, everything is mapped to the zero vector of the codomain, zero vector of the codomain, or a surjective map, in which case it's one-dimensional, a surjective map. Okay. Therefore, f star comma p fails to be surjective if and only if the matrix representing it is, so in the latter case it's going to be a surjective map, right? In which case the image is one-dimensional. So so this linear map fails to be surjective if and only if the matrix representing this linear map is just a zero matrix. Okay, so this matrix is the zero matrix, which means that all the entries in this row vector are identically zero. That is, all the partial derivatives del f by del xi at p vanish. Okay, QED. Good. Now, I did not give this figure. So this is the figure for a donut, for the height function on two torus. Okay, so these are the critical points. So let me draw the picture first. So figure, this is the caption, critical points, and critical values of the height function what is the height function? Fxyz is equal to simply z. Okay, we pick up the z coordinate of the two torus. So here is the real line, the z-axis. So this is going to be the image of this point here on R, and this is the image, this is the image of that point, and this is the image of this point. Okay, right? So x, y, z are points on the torus, on the two torus, and this image are these images, the image of f um, is in R, right? So the if I take the differential of this map, then it fails to be surjective at these uh, 4 points only, right? In which cases, in which cases um, the images are just a zero-dimensional subspace of R uh, containing one point, the zero vector of the real line. Okay, in all other cases, um, the image will be a one-dimensional subspace of R, which is R itself, right? So these are the 4 critical points of the height function on two torus. Okay, all right. So now it's time to mention a few exercises, suggested exercises. Page 98, problem number 8.1, 8.2, 8.4, 8.6, and 8.8. Okay, all right, so this is it. So this is the end of lecture 6. In the next lecture, we will begin discussions on regular submanifolds. Okay, thank you for attending the 6th lecture.